Last class exponential functions in the classical definition I am discussing E is E of x, that is E raised to x. This is increasing function, strictly increasing differentiable and differentiable on R. So it has a inverse. When it continues and strictly monotonic inverse under, therefore E has inverse from the range. Range of E of R range E of R real numbers in the images. Okay, so that will be the positive real numbers. Okay, that is R plus. So from this R plus we can define the inverse function. We call it as L. Okay, so this is also strictly increasing. When E increasing L strictly increasing over and L is also differentiable. So we have some properties from this in this function itself. So we define this from R plus to R. Okay, such that E composition L equal to identity function. That means E composition L of some y equal to y itself for all y belongs to R plus. Okay, so this is the definition. This is in the other way we can write E of L of y equal to y for all y greater than 0. This is the other way to define this function. Equivalently you can get L of E of x, that is x itself for all real numbers x which belongs to R. Okay, so now you differentiate this, you can get L dash. Derivative of this is L dash of E of x into E dash of x equal to 1, because the derivative with respect to x is 1 from the right hand side, and E dash x we already proved that E dash x equal to E of x itself. So L dash of E of x equal to this is same as E of x itself. So this is same as E of x, that is equal to 1. So what is the consequence? L dash of E of x will be 1 by of x. So if you replace this E of x by y, we can write L dash of y equal to 1 by y for all y greater than 0. So derivative of this L is this 1 by y. Okay, now take x equal to 0 in the equation written here, L of E raised to x equal to in this equation I call it as some equation number 1. So in 1 take x equal to 0. In 1 we have this L of E of 0 equal to 0. That implies L of E of 0 is 1. So L of 1 is 0. Okay, now you consider this L dash of y equal to 1 by y. So integrate both sides. Integrate both sides from 0 to 1 to y, not 0 to y, 1 to y, L dash y dy, differentiating this equation. That will be integral 1 to y, 1 by y dy. So that implies when you differentiate, integrate this, you can get L of y, that is from 1 to y. So that is L of y minus L of 1. And right side will be integral 1 to y, integral 1 to y dx by x. Okay, so this is integral 1 to y dx by x or dy by y, both will be the same. So we write since L of 1 is 0, then L of y takes the form integral 1 to y dt by t or dx by x or dy by y itself. Okay, so these are the dummy variables. So this is the definition of this L of y. Therefore, this equation is taken as the starting point of the theory of logarithmic function. Okay, so this is going to be some log of something. So before that, we observe some other properties. If we write u is equal to some e of x and v is equal to some e of y, then we know that what is this by definition of by the properties of E, what is L of u times v here? That is L of E of x into E of y. Okay, from this, then we can write L of E of x plus y, because E of x and E of y, by the property of E, you can write like this. And when you get this L and your inverse function, then this will be x plus y. Okay, so what is x? X is this x is going to be the by taking L on both sides from this equation, L of u will be L of E of x, that is x. So x can be written as L of u and y can be replaced as L of v. So we have L of u uv, L of u times v will be L of u plus L of v. So this is the property of this inverse function. This is true for all positive values, u greater than 0 and v greater than 0. Okay, so this is a useful equation. Now we write this L function L of y as our log y. Okay, so we just put this symbol, or you can write L of x equal to log x. So if you put, we write this inverse function as log of this, okay, log of x. Now we say that we can get as x tends to infinity, this log x tends to infinity. So this log x tends to infinity, and so these are the interesting consequence of this capital L inverse function. So you can easily find out all these things using the property of E itself. Okay, now we have for x greater than 0, similarly you can get as x tends to 0, we have log x tends to minus infinity. So using the properties of E, we already discussed the properties of E as x tends to infinity and minus infinity, so you can easily usually get these consequences. So now we take a positive quantity x greater than 0 and n is an integer, for n belongs to z, then we have what happens to this x raised to n. So x raised to n can be written as this is equal to e of L of x raised to n. Okay, because E and L are inverse functions. So this will be E of L of x raised to n can be at least L of x plus L of x plus n times. So that is m times L of x. Okay, now using this fact, you can get this. This is true for every x greater than 0 and n belongs to z. Now we write this is x raised to 1 by m. The same thing happens. This is E of L of this L of x to the power 1 by m. So this can be written as E of 1 by m times L of x. Okay, so using this fact, you can get any alpha. For any alpha belongs to Q, we have this x raised to alpha can be written as E of alpha power alpha times L of x. Okay, so these are because of these facts. We know that what is m times L of x raised to 1 by m. Okay, we know that this is L of x raised to 1 by m plus L of x raised to 1 by m plus etc. So this is m times, so plus etc. plus L of x raised to 1 by m, m times So this can be written as L of x raised to 1 by m into x raised to 1 by m into etc. x raised to 1 by m times. So this is our L of x. Okay, now applying so from this you can write L of x raised to 1 by m is equal to 1 by m times L of x. Okay, so by applying this E on both sides, we have E of this L of x raised to 1 by m, that is x raised to 1 by m, that is E of 1 by m L of x. Okay, so that is this is nothing but this result. Similarly, if we combine these two things, then we can get the this is true for every rational numbers. Alpha, if we take alpha as n by m and apply the same results, then we can get x raised to alpha is equal to E of L of x. Okay, so but we write this as E of something is E power something. So E power alpha times L of x is log x. Okay, so for any alpha, any rational number alpha, x raised to alpha can be written as E to the power alpha log x. So this is true for every rational numbers. Okay, so obviously we can extend this to the real numbers, any real numbers. So because the irrational numbers are the limit points of these rational numbers, so we can get for any real alpha, any alpha belongs to R, we can get this result. X raised to alpha is nothing but E to the power alpha log x. Okay, so this is true for every real number alpha. Okay, now we have the derivative. So using the this is because of the continuity of these functions. So similarly, we can consider these are the usual logarithmic and the exponential functions of real numbers. Now we have the derivative. What is x raised to alpha? Derivative of this x raised to alpha. So that is nothing but E of alpha L of x times alpha by x. Okay, this is because the derivative of E of something is E of alpha L of x itself, and derivative of this is derivative of alpha L of x is alpha times derivative of L of x. Derivative of L of x is L dash x. L dash x is 1 by x. Okay, so that will give this one. Now you can write this as E of alpha of L of x. That is alpha times, this can be written as alpha times x to the power alpha minus 1. Okay, so this is this define using these properties of alpha and E, L and E, you can get the derivative of x raised to alpha for any real number alpha. If we want to have the integer, any real number alpha we have that is alpha times x raised to alpha minus 1. That is because this is itself x raised to alpha, so we replace this quantity by x raised to alpha, you can get x raised to alpha minus 1 into alpha, so that will give this derivative. Okay, so now we discuss an important property of this function, that is nothing but the limit extends to infinity, x to the power minus alpha and log x. What is this limit? We will prove that this limit is 0. Okay, so this is true for every alpha greater than 0. Okay, that means log x by x raised to alpha, so positive alpha is always limit 0 as x tends to infinity. Okay, so that is the meaning of this. For this we consider epsilon for if we consider 0 less than epsilon less than alpha and x greater than 1, then what is x raised to minus alpha log x? That is x raised to minus alpha. By definition, this is interval 1 to x 1 by t dt, but this is less than x raised to minus alpha integral 1 to x this t to the power epsilon minus 1. Okay, so this is because this is in fact t to the power minus 1, so we compare two functions t to the power minus 1 and we need to compare these two quantities t to the power minus 1 and t to the power epsilon minus 1. Okay, since this epsilon is positive, this quantity can be replaced. This is t raised to epsilon into t raised to minus 1. So we can say that this is this t raised to epsilon is greater than 1 because t is greater than 1. So this interval is from 1 to x. So t is in between 1 and x. Then t to the power epsilon is greater than 1. Now 1 dash epsilon, that is 1. So we can have we can get this inequality. Therefore we can get this inequality for integrals as well. Okay, now we have this is equal to, the right hand side will be equal to x raised to minus alpha. By integrating this you can get x raised to epsilon minus 1 divided by epsilon, and which is less than x to the power epsilon minus alpha divided by epsilon. Okay, so as x tends to infinity, since this alpha is we have taken this alpha is greater than epsilon, so epsilon minus alpha is always negative number. So this can be written in the denominator as x tends to infinity, that going to be 0. This right hand side going to be 0. Then we can say that this limit happens, limit x tends to infinity, x raised to minus alpha into log x will be 0 because of this inequality. Okay, so these are some interesting properties of the inverse of e of x, that is log x. Okay, in the next class we will discuss the trigonometric functions.